MPIA, so the Max Planck Institute of Astronomy in Heidelberg. We have a sustainability group, very active. And today I'm talking on behalf of them and also Knut Janke, who's here. And just to give you an idea, so our MPIA is mid-sized institute with 150 researchers, and we assessed how much CO2 we emit per researcher. And this is part of the data that we take here. I'm sorry, my Slack channel can be seen. So the data is taken from the article, the Nature Astronomy article in 2020, and we since refined our analysis. So the numbers slightly changed. But let me talk you through the numbers. So for flying per year and per astronomer, we emit 4 tons of CO2. That's pre-pandemic. For electricity, we use 5 tons of CO2, and supercomputing makes up 80% of that. But if we if we use the German CO2 intensity of electricity production, then it would actually be double that, because Heidelberg and Munich city grids buy a lot of renewable energies. So heating, that's a specialty of our institute, because we are located in a brutalismus building with concrete walls and no insulation. So that's 3 tons, and commuting for us is 1 ton. And we haven't assessed infrastructure, or we didn't do life cycle assessment. So infrastructure and life cycle is a big question, but my pre-speakers, they were going into the infrastructure of observatory details. So that's quite complementary. And just for comparison, the German yearly average is 10 tons, and the German pledge for 2030 is to reduce to 5 tons. So we only work related are already producing 13 tons of CO2. So we really need to reduce. Shortly putting supercomputing into perspective. So the German average uses 6 megawatts hours per year. And as an astronomer, we use about 20 megawatt hours per year for our supercomputing needs. And if we break this down to how many cores we are using, that's around 200 cores running non-stop, 2.3 kilowatts of power, and that's equivalent to 2 vacuum cleaners for each astronomer running all year long. But that, of course, is an average. So we really have a few super users, but also a lot of data processing that needs a lot of computations. So for flying, we have this nice animation from our Python pipeline that analyzes our business travels, and you see where we are all going. And you will also see that there's a strong decline with the pandemic. And the major breakdown of this is shown in this graph. So 15% of our trips go overseas, so to other continents. And those 15% emit 82% of our CO2. That means we need to cut long distance trips to be able to lower our CO2 emissions. The way forward now. So we have done the assessment. We know our main CO2 emissions. It's flying, computing, and maybe observing infrastructure. So we need goals. We need to set a reduction timeline and set it per category and make overall goals. So if we go with a general policy, we should aim at 50% less by 2030 and net zero by 2040. The action is now the crucial thing. We need to take action. We need to make reduction plans and implement those plans and change our habits. So we need to look to have travel policies on the institute, as an institute, and change our workshop formats, and also think about computing policies. So this is something, that we really need to think of. And I think also monitoring those. So we need to monitor our emissions and evaluate our policies and readjust them on a yearly basis. So as an astro community, and we are an international community, and we have a lot of resources. So we really need to think about our responsibility, and we need to think how we actually organize conferences and our collaborations and also our committees. We need to create low carbon networking possibilities especially for early career researchers. We need to think about how to value the achievements of applicants. So is it worthwhile to get many talks invitations and go over the globe, or what how do we value those? So we also need to plan processing needs and data centers. Where do we build them? And yeah, we need to plan simulations. It doesn't make sense to make big cosmological simulations twice. We also need to think about how we code, and do we employ people for coding? Because if we have people permanent positions for that, then the code will also be maintained and optimized, and that's important. And generally, we should include carbon emissions into our project decisions, as we have seen before. So a few general or personal measures that we have for flying is: don't fly, use virtual participation or the train, and yeah, don't fly intercontinental, that dominates the emission. When flying, try to make out most of your stay. So I think changing continents should be something that we do for years. So that means only moving to another continent, and or in exceptional cases. And we should integrate remote participation when organizing a meeting, because most of the emissions is coming from a few very far flyers, and if they can join remotely, that already helps a lot. For computing, we have the following ideas. We need to evaluate our data and processing demands when planning the experiments. We need to reduce our CO2 intensity of electricity, use renewables, or change to a location where there's a lot renewables. And also we need to be able to use the electricity when it's mostly produced by renewables. So adapt with daytime, or yeah. We need to improve our utilization rate and try to reduce our hardware. Reduce the data volume. So we need to think about loss compression. There are a lot of interesting ideas. We need to share expensive simulations within the scientific community, and also use our computing waste heat. GPU usage can help, and also efficient programming that should be taught. So in essence, this is a call to action. We really need to be fast and move our field. How can we work in a low carbon world? How can we get there? And also, how can we get there very fast? Thanks for your attention.